You've been lied to. Not maliciously, but fundamentally. Every textbook, every science video, every teacher who told you that gravity only pulls on things with mass was technically correct, but catastrophically incomplete. Right now, photons from distant stars are streaming past Earth, weightless particles that should laugh in the face of gravity. Yet in 1919, Arthur Eddington pointed a telescope at a solar eclipse and watched starlight bend around the sun. Impossible. Light has no mass. Gravity pulls on mass. But there it was, documented, photographed, undeniable. The universe doesn't care about our logic. Here's the thing that should make you pause your entire day. Black holes trap light completely, not just bend it, not just slow it down. They grab photons traveling at 186,282 miles per second and stop them cold. These are particles with zero rest mass, zero weight, zero business being affected by gravity, according to Newton's laws. Yet they're prisoners. And the reason why reveals something so disturbing about the nature of space, time, and reality itself that once you understand it, you'll never look at an empty room the same way again. What if I told you that gravity isn't even a force? That every moment of your life, you're not being pulled down but pushed up? That the earth beneath your feet is accelerating upward into you right now? And the only reason you don't notice is because space itself is twisted into a shape your brain literally cannot visualize. This isn't metaphor. This is Einstein's general relativity, and it's been tested more thoroughly than almost any theory in physics. And once we unpack why black holes trap light, you'll understand why you're not standing still right now, why time runs slower near massive objects, and why the universe might be fundamentally stranger than any science fiction. Before we dive into this rabbit hole together, do me a favor. Hit that like button, smash subscribe, and tell me in the comments what country you're watching from and what time it is there right now. I want to know how many people around the world are about to have their minds reconstructed, because in the next 3 hours, we're going to dismantle everything you think you know about gravity, light, space, and time, then rebuild it into something far more beautiful and terrifying. Let's start with the most basic question that contains the seeds of everything. What exactly is light? For thousands of years, humans thought light was instantaneous. You open your eyes and you see. Simple. And in 1676, a Danish astronomer named Ole Ratmer was studying Jupiter's moons and noticed something weird. When Earth was moving toward Jupiter, the moons appeared to orbit faster. When Earth was moving away, they slowed down. Not because the moons were actually changing speed, but because light took time to travel. Ratmer calculated that light moved at about 220,000 kilometers per second. He was off by about 25%, but he'd shattered a fundamental assumption. Light travels, which means it moves through space, which means it should behave like other things that move. Newton thought light was made of particles, tiny corpuscles shooting through space. His contemporary, Christian Huygens, argued light was a wave. They were both right and both wrong, but we'll get to that brain melter later. For now, just focus on this. Whatever light is, it moves at a finite speed. And here's where things get interesting. If light is particles, those particles have to have mass, right? Everything that exists has mass. Except light doesn't. Zero. Zilch. A photon weighs nothing. You might think, well, it must weigh something tiny. No, not tiny. Zero. This isn't a measurement problem. Photons have literally zero rest mass. If they had any mass at all, even a billionth of a gram, we'd detect it. We haven't. Photons are bundles of pure energy with no mass. They're the universe's way of saying, mass is optional. But here's the twist that kept physicists up at night. If photons have no mass, how do they have momentum? When sunlight hits a solar sail in space, it pushes it. That's momentum. Momentum requires mass and velocity, right? Momentum equals mass times velocity. but photons have zero mass. 0 times anything is 0. So how are they pushing solar sails? The answer reveals something profound about the relationship between energy and momentum. Einstein showed that photons have momentum not because they have mass, but because they have energy. And in relativity, energy and momentum are two sides of the same coin. The momentum of a photon equals its energy divided by the speed of light. This works perfectly with observations, but it requires you to abandon the Newtonian idea that only massive things can push other things. Think of it like this. Imagine you're in a completely dark room and someone throws perfectly silent balls at you. You'd feel them hit and know something was there, even though you couldn't see or hear them. Now imagine someone shines a flashlight at you. You wouldn't feel it. But if that flashlight was powerful enough, billions of times more powerful, you would. Photons carry momentum without mass, which means they can affect the physical world despite being weightless. This is our first hint that the universe doesn't play by the intuitive rules we think it does. Mass isn't required for influence. Energy alone can push things around. But if that's true, why would gravity care about photons? Newton's gravity pulls on mass. No mass, no pull. End of story. Except it's not the end. It's barely the beginning. Let's talk about Isaac Newton for a moment, because we need to understand what he got right before we can appreciate what he got catastrophically wrong. In 1687, Newton published the Principia Mathematica, arguably the most important scientific book ever written. In it, he described universal gravitation. Every mass attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. This was revolutionary. Before Newton, people thought objects fell because that's where they belonged, or because nature abhors a vacuum, or because God willed it. Newton gave us math. He showed that the same force pulling an apple down also keeps the moon orbiting Earth and Earth orbiting the sun. One law for everything. Elegant, beautiful, and it worked. Using Newton's equations, astronomers predicted the existence of Neptune before anyone saw it, just by watching irregularities in Uranus's orbit. They predicted the return of Halley's Comet. They sent men to the moon. Newtonian gravity is accurate enough for almost everything we do, but almost everything is doing some heavy lifting there. Here's the problem. Newton's gravity is a force that acts instantly across space. If the sun suddenly vanished, according to Newton, Earth would immediately fly off in a straight line. Not 8 minutes later when the last sunlight reached us. Immediately. Instantaneous action at a distance. Newton himself hated this aspect of his theory. He wrote that one body may act upon another at a distance through a vacuum without the mediation of anything else is to me so great an absurdity that I believe no man who has any competent faculty of thinking can ever fall into it. But he couldn't figure out an alternative, so he published the math and left the mechanism as a mystery. For over 2 centuries, physicists used his equations and ignored the philosophical problem. Then in 1905, a 26-year-old patent clerk in Switzerland published a paper that would demolish the idea of instantaneous action forever. Albert Einstein's special relativity showed that nothing, no force, no information, no influence of any kind can travel faster than light. The speed of light isn't just a speed limit for things moving through space. It's a fundamental limit on causality itself. Think about what this means for gravity. If the sun vanished, its gravitational effect couldn't instantly disappear. That information would have to travel to Earth, and it couldn't travel faster than light. So gravity must propagate at the speed of light or slower. But if gravity propagates, if it travels through space like light does, then what is it traveling through? Newton's gravity was a force between masses across empty space. But special relativity suggested something had to be carrying that force. Einstein spent the next 10 years obsessing over this problem. How does gravity work if it can't act instantaneously? What carries gravitational force? And here's the question that led him to his greatest insight. If gravity is a force that pulls on mass, and light has no mass, why did starlight bend when it passed near the sun? We're about to enter territory where language itself starts to fail, where the metaphors we use aren't quite right, because human brains didn't evolve to understand what's really happening. But stay with me, because what Einstein discovered is so elegant, so perfectly beautiful, that once you see it, everything else makes sense. Gravity isn't a force at all. It's geometry. Imagine you're an ant walking on a stretched rubber sheet. From your perspective, you're walking in a straight line. But if someone places a bowling ball on the sheet near you, it creates a depression, and your straight path curves around the depression. You're not being pulled by a force. The surface you're walking on is curved, so your straight line in that curved surface looks like a curve from outside. This is the analogy everyone uses for general relativity, and like all analogies, it's imperfect. The rubber sheet is being pulled down by gravity, which is the thing we're trying to explain. But bracket that for a moment. The core idea is right. What we call gravity is the curvature of space itself. Einstein's breakthrough was realizing that space and time aren't separate things. They're woven together into a four-dimensional fabric called spacetime. Massive objects don't pull on other objects. They warp the geometry of spacetime around them. Other objects moving through that warped spacetime follow the straightest possible paths, called geodesics, but because the space is curved, those paths look curved to us. Here's the truly wild part. You're not being pulled down right now. You're trying to move along your natural geodesic through spacetime, which is a straight line upward through time. But Earth's mass has curved spacetime around you, and your geodesic intersects with Earth's surface. The ground is literally accelerating up to intercept your path through spacetime. The force you feel isn't gravity pulling you down. It's the ground pushing you up, preventing you from following your natural path. This sounds insane. It feels wrong. But it's been confirmed by every experiment we've thrown at it. When Einstein published his field equations in 1915, he made 3 predictions that could test his theory. First, he explained a peculiarity in Mercury's orbit that Newton's gravity couldn't account for. Mercury's orbit precesses, meaning its ellipse slowly rotates. Newton's equations predicted one rate. Observations showed a slightly different one. Einstein's equations nailed it exactly. Second, he predicted that clocks run slower in stronger gravitational fields. Time itself is affected by mass. This wasn't just theory. In 1971, physicists flew atomic clocks on airplanes around the world. The clocks at altitude, where gravity is slightly weaker, ran faster than identical clocks on the ground by exactly the amount Einstein predicted, down to the nanosecond. GPS satellites have to account for this time dilation, or they'd be off by miles within hours. Third, and most relevant for our question, Einstein predicted that light would bend when passing near massive objects. Not because photons have mass and are being pulled, but because the space the photons are moving through is curved. Photons always travel in straight lines through spacetime, but if spacetime is curved, those straight lines are curved too. In 1919, Arthur Eddington led an expedition to observe a solar eclipse. During totality, stars near the sun's position in the sky became visible. If Newton was right, their light shouldn't bend significantly. If Einstein was right, their apparent positions would shift by a specific amount. Eddington's photographs showed the shift. Headlines around the world proclaimed Einstein's theory triumphs. Newton's 250-year reign was over. But here's what's crucial to understand. The light isn't being pulled. There's no force acting on the photons. They're just traveling in straight lines through curved space. From the photon's perspective, if a photon could have a perspective, it's going perfectly straight. Space itself is bent. This is why black holes can trap light. Now we're ready to understand the real answer. What is a black hole? It's not a hole. It's not a cosmic vacuum cleaner. It's the ultimate conclusion of Einstein's equations when you ask, what happens if you compress enough mass into a small enough space? Imagine you're standing on Earth's surface. Earth's mass curves space-time around it, creating what we experience as gravity. Now imagine Earth was compressed to half its radius, but kept all its mass. The surface gravity would be stronger because you'd be closer to all that mass. Compress it smaller, gravity gets stronger. Keep going. At some point, the curvature of spacetime becomes so extreme that the escape velocity, the speed you'd need to break free, exceeds the speed of light. That point is called the event horizon, and the object creating it is a black hole. Here's the key insight. The event horizon isn't a physical surface. It's a boundary in spacetime, beyond which all paths lead inward. It's not that gravity is pulling so hard that light can't escape. It's that spacetime is curved so severely that every direction points toward the center. Imagine you're at the North Pole. No matter which direction you walk, you go south. At the event horizon, no matter which direction you move through time, you move toward the singularity. Let me say that again, because it's probably the most important sentence in this entire script. Inside a black hole's event horizon, all paths through time lead to the center. The singularity isn't just in your future, the way tomorrow is in your future. It's in your future the way 1 second from now is in your future. You can no more avoid hitting the singularity than you can avoid experiencing the next moment. This is what it means for light to be trapped. Photons still travel in straight lines through spacetime. But spacetime is curved so intensely that those straight lines spiral inward. The photon isn't being slowed down or pulled back. It's moving at the speed of light along its natural path. But that path only goes one direction, toward the singularity. In 1916, just months after Einstein published his field equations, a German physicist named Karl Schwarzschild found an exact solution to Einstein's equations for a non-rotating black hole. He was serving in the German army during World War I and did the math in trenches between artillery bombardments. He calculated the radius at which an object's escape velocity equals the speed of light, now called the Schwarzschild radius. For Earth, it's about 9 millimeters. If you compress the entire Earth to the size of a marble, it would become a black hole. For the Sun, it's about 3 kilometers. Schwarzschild died of a disease he contracted on the Russian front, just months after publishing his solution. He never knew his equations predicted some of the most extreme objects in the universe. For decades, physicists thought black holes were mathematical curiosities, not real things. They seemed too weird, too extreme. But in 1964, an X-ray detector on a rocket flight discovered an intense X-ray source in the constellation Cygnus. Optical observations showed a bright blue star orbiting something invisible. By measuring the star's motion, astronomers calculated the mass of its companion. At least 15 solar masses, far too heavy to be a neutron star. It had to be a black hole. We now call it Cygnus X1, and it was the first black hole we found. Since then, we've discovered thousands. We've detected gravitational waves from colliding black holes. We've photographed the supermassive black hole at the center of the M87 galaxy, 55 million light-years away, revealing the glowing accretion disk and the shadow of the event horizon exactly where Einstein's equations predicted. Black holes are real. They trap light. And the reason has nothing to do with force or pulling or attraction. It's pure geometry. Space is curved so severely that escape is geometrically impossible. But here's where things get really weird, and I need you to stick with me, because this is where most explanations fail. When we say space is curved, what does that actually mean? You can visualize a two-dimensional surface being curved in 3 dimensions. You can imagine a rubber sheet bending. But space-time is 4-dimensional, and it's being curved not into some external 5th dimension, but within itself. There's no outside perspective from which to view the curvature. The curvature is intrinsic. Here's an analogy that might help. Think about the surface of a sphere, like Earth. From an ant's perspective walking on the surface, space seems flat locally. But if the ant walks far enough in what it thinks is a straight line, it ends up where it started. The surface has intrinsic curvature. There's no third dimension the ant can access or even conceive of, but the curvature is real and measurable. Space-time is like that, but harder to visualize because we're embedded in it. We can't step outside to see the curvature, but we can measure it by watching how objects move and how time flows. Here's what will blow your mind. Near a black hole, time slows down from the perspective of distant observers. If you watch someone fall toward a black hole's event horizon, you'd see them slow down, redden, and fade, never quite reaching the horizon. From their perspective, they'd cross it in finite time, but from yours, it takes forever. This is time dilation, not as a side effect of gravity, but as a manifestation of space-time curvature. The curvature affects not just space, but time. Near massive objects, time runs slower. At the event horizon of a black hole, time dilation becomes infinite. A clock at the horizon appears, frozen from outside. But from the perspective of something crossing the horizon, time flows normally. You'd cross the event horizon without noticing any particular moment when it happened, except that you'd realize you could see the entire future history of the universe compressed into a final instant as you fell toward the singularity. This reveals something profound. Time and space are intimately connected. The distinction between past, present, and future is, as Einstein put it, a stubbornly persistent illusion. Space-time is a four-dimensional block, and what we experience as the flow of time is our consciousness moving through it, like reading a book page by page even though the entire book exists simultaneously. Now, let's connect this back to light. A photon doesn't experience time. Because it travels at the speed of light, time dilation is total. From a photon's perspective, if it had one, it's emitted and absorbed in the same instant, even if it travels for billions of years from our perspective. The photon exists at all points along its path simultaneously. When a photon crosses a black hole's event horizon, from our perspective, it seems to freeze at the horizon. From the photon's timeless perspective, it reaches the singularity instantly. Both perspectives are equally valid. Reality is the four-dimensional space-time structure. Our experience of it is just one way of slicing that structure into space and time. This is getting abstract, so let me ground it with something concrete. If you could somehow survive near a black hole and send light signals back to Earth, your signals would be redshifted, meaning their wavelength would stretch, their energy would decrease, and they'd arrive slower and slower. Eventually, you'd cross the event horizon, and your signals would never escape. But you'd keep experiencing time normally. You'd see Earth's future unfold and fast forward as you fell toward the singularity. The question, why do black holes trap light, has an answer, but it's not simple. Light is trapped because space-time curvature is so extreme that all future-directed paths lead inward. Photons follow straight lines through curved space-time, and those lines converge on the singularity. There's no force, no pulling, no violation of the principle that light has no mass. Just geometry. But this raises a deeper question. What is the singularity? At the center of every black hole, according to Einstein's equations, is a singularity, a point where curvature becomes infinite, where density becomes infinite, where our equations break down and produce nonsensical results. This is where general relativity fails. It's not that we don't know what happens at the singularity. It's that the theory tells us we can't know because the theory itself stops working. Many physicists believe the singularity isn't real, that it's a sign we need a theory of quantum gravity to describe what's actually there. String theory, loop quantum gravity, and other approaches suggest the singularity might be replaced by something else, some kind of quantum structure that avoids infinite density. But here's the thing, we can't observe it. The event horizon shields the singularity from the outside universe. This is called cosmic censorship, and it's one of the most important ideas in black hole physics. If singularities existed without event horizons, naked singularities, they'd be regions where physics breaks down that we could observe. That would be catastrophic for science. The universe seems to conspire to prevent that by always wrapping singularities in event horizons. Roger Penrose proved theorems in the 1960s showing that singularities are inevitable given certain reasonable assumptions. Stephen Hawking extended this work to show that the Big Bang itself was a singularity. For this work on black holes and singularities, Penrose won the Nobel Prize in Physics in 2020. Hawking made another discovery that's even more mind-bending. Black holes aren't entirely black. They radiate. In 1974, Stephen Hawking was applying quantum mechanics to black holes and discovered something shocking. According to quantum field theory, empty space isn't truly empty. Virtual particles constantly pop into existence in pairs. A particle and its antiparticle then annihilate each other almost immediately. This happens everywhere, all the time, and it's been confirmed in labs through something called the Casimir effect. Near a black hole's event horizon, something strange can happen. If a particle-antiparticle pair appears right at the horizon, one particle might fall in while the other escapes. To a distant observer, it looks like the black hole emitted a particle. This is Hawking radiation. Here's the truly weird part. The particle that escapes has positive energy. The particle that fell in must have negative energy to conserve energy overall. Negative energy decreases the black hole's mass. Over immense timescales, longer than the current age of the universe for stellar mass black holes, this process causes black holes to evaporate. This creates a paradox that physicists are still arguing about: information. Quantum mechanics says information can't be destroyed. But if something falls into a black hole and the black hole eventually evaporates, where did the information go? Hawking radiation is thermal, meaning it carries no information about what fell in. This is the black hole information paradox, and it's one of the biggest unsolved problems in theoretical physics. Some physicists think information is encoded in subtle correlations in the Hawking radiation. Others think it's stored at the event horizon in a holographic way, meaning the three-dimensional information is encoded on the two-dimensional horizon surface. Still others think there are no true singularities, and information re-emerges when quantum gravity kicks in. The point is, we don't have all the answers. Black holes sit at the intersection of general relativity, quantum mechanics, and thermodynamics, three pillars of modern physics that don't quite fit together. Solving the puzzles black holes present might require a revolution as big as relativity or quantum mechanics themselves. And that brings us to an even deeper question. If space-time can be curved, what is it? What is this fabric that bends and twists? Is it made of something? Does it have structure at the smallest scales? Einstein's general relativity treats space-time as a smooth continuum, infinitely divisible. But we know from quantum mechanics that everything else in nature is quantized, comes in discrete units. Light comes in photons. Matter comes in atoms. Energy levels are discrete. Is space-time quantized too? Some theories say yes. Loop quantum gravity, for instance, proposes that space-time has a granular structure at the Planck scale, about 10 to 35 meters, far smaller than anything we can probe with current technology. At that scale, space-time might be a network of discrete loops, and what we perceive as smooth space is an emergent property, like how a smooth image on a screen is made of individual pixels. String theory takes a different approach. It proposes that the fundamental constituents of reality aren't particles, but tiny vibrating strings. Different vibration modes correspond to different particles. Space-time itself emerges from the relationships between these strings. In string theory, there aren't three dimensions of space and one of time. There are 10 or 11 dimensions, most of which are curled up so small we can't detect them. These theories make testable predictions, but the energies required to test them directly are far beyond our reach. We'd need particle accelerators the size of galaxies. So physicists look for indirect evidence in cosmology, in black holes, in the very early universe. But here's what's important for understanding why black holes trap light, regardless of whether space-time is fundamentally smooth or granular, made of strings or loops or something else entirely. At the scales we can observe, it behaves according to Einstein's equations. And those equations tell us that mass energy curves space-time, and objects follow geodesics through that curved space-time, light included. Now, let's address something that might be bothering you. If gravity isn't a force, why do we talk about gravitational force? Why do physicists use Newton's equations for most calculations? The answer is that Newton's theory is an approximation that works brilliantly in weak gravitational fields and at low speeds. For everyday purposes, for launching satellites, for calculating planetary orbits, Newton's equations are simpler and good enough. General relativity reduces to Newtonian gravity in the appropriate limits. It's like how chemistry doesn't need quantum mechanics for most purposes, even though atoms are fundamentally quantum. You can predict chemical reactions using classical models because the quantum effects average out at large scales. Similarly, you can predict orbits using Newton because the curvature effects are small. But near black holes, near neutron stars, during the Big Bang, in the very early universe, you absolutely need general relativity. The differences aren't subtle, they're dramatic. And this brings us to something you might not have considered. If black holes curve space-time so intensely, and if the universe contains billions of black holes, plus all the other mass and energy distributed throughout space, what does the large-scale structure of the universe look like? The universe is expanding. We've known this since 1929, when Edwin Hubble observed that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. This isn't because they're moving through space. Space itself is expanding, carrying galaxies along with it. General relativity predicted this. When Alexander Friedmann and Georges Lemaître applied Einstein's equations to the universe as a whole, they found solutions where space could be expanding or contracting. Einstein initially added a cosmological constant to keep the universe static because he, like everyone at the time, assumed the universe was eternal and unchanging. When Hubble's observations showed expansion, Einstein called the cosmological constant his biggest blunder, except it wasn't. In 1998, two teams of astronomers studying distant supernovae discovered that the universe's expansion is accelerating. Something is pushing space apart, and we call it dark energy. The cosmological constant, a kind of energy inherent to space itself, is the leading explanation. Einstein's blunder might be one of his greatest insights. Dark energy is bizarre. It has negative pressure, which in general relativity means it pushes space apart rather than pulling it together. It makes up about 68% of the total energy of the universe. Dark matter, which we detect through its gravitational effects but can't see, makes up about 27%. Ordinary matter, everything we can see, all the stars, planets, gas, dust, you, me, everything, is only about 5%. We live in a universe where 95% of its contents are invisible and mysterious. Now, here's where it connects to black holes and light. The large-scale structure of the universe is determined by the interplay between gravity, which pulls matter together, and dark energy, which pushes space apart. On small scales, gravity wins, forming galaxies, stars, and black holes. On large scales, dark energy dominates, driving expansion. Light traveling through this expanding universe gets stretched, redshifted. The farther light travels, the more space expands during its journey, the more it's redshifted. We can use this to measure distances to distant galaxies. But here's something that's going to mess with your head. If space is expanding, what's it expanding into? Nothing. It's not expanding into anything. Space itself is growing. There's no outside. The universe isn't a sphere expanding in some higher dimensional space. The universe is everything, and everything is getting bigger. Similarly, when we say a black hole curves spacetime, it's not bending into some external dimension. The curvature is intrinsic, defined by the geometry itself. This is hard to conceptualize because our brains evolved to understand three-dimensional space from an outside perspective. We can't visualize four-dimensional spacetime or intrinsic curvature without embedding it in something else. But mathematically, it's perfectly consistent. And here's the truly wild implication. If the universe is finite but unbounded, like the surface of a sphere, you could, in principle, travel in a straight line and eventually return to where you started. Whether our universe has this geometry or is infinite and flat is still an open question. Current observations suggest it's very close to flat, but we can only observe a finite portion, about 93 billion light-years across. Beyond that is the rest of the universe, which we can never observe because light from those regions hasn't had time to reach us and never will because of the accelerating expansion. There's a cosmic event horizon, regions of space that are receding so fast that light from them will never reach us. This means there's a fundamental limit to knowledge. There are parts of reality we can never access, not because of technological limitations, but because of the structure of spacetime itself. Just like the inside of a black hole's event horizon. In both cases, light can't escape because of spacetime geometry. For a black hole, it's curvature. For the cosmic horizon, it's expansion. But the principle is the same. Geodesics, the paths light follows, don't connect those regions to us. This is the deep answer to why black holes trap light. Spacetime itself determines where light can and cannot go, and in a black hole's case, all paths lead inward. But let's bring this back to something more immediate. How does this affect you? You're made of atoms that were forged in stars. Every carbon atom in your body, every oxygen atom, every atom heavier than hydrogen and helium, was created in the fusion furnaces of stars or in the supernova explosions that ended those stars' lives. You are literally stardust. Some of those stars collapsed into black holes. The matter that didn't fall in was ejected into space, seeding molecular clouds where new stars and planets formed. The solar system Earth, and you exist because stars died, some of them violently, some of them collapsing into black holes. The atoms in your left hand might have come from a different star than the atoms in your right hand. You're a collection of debris from cosmic catastrophes, assembled by gravity into a structure complex enough to contemplate its own origins. Now, knowing what you know about spacetime curvature, realize this. You are constantly falling. Your natural path through spacetime is a geodesic that would take you in a parabolic arc, but Earth's mass curves spacetime such that your geodesic intersects the ground. The ground pushes you up, accelerating you at 9.8 meters per second squared, which you experience as weight. When you're in, why is there something rather than nothing? Why does the universe exist? Why do the laws of physics have the form they do? Why is spacetime four-dimensional? Why does mass energy curve spacetime according to Einstein's specific equations and not some other relationship? Physics can't answer these questions. Science describes how the universe works, not why it exists. But we can explore the question. One possibility is the anthropic principle. The universe has properties compatible with conscious observers, because if it didn't, we wouldn't be here to observe it. This seems like a tautology, but it has bite. If the constants of physics were slightly different, stars wouldn't form, atoms wouldn't be stable, chemistry wouldn't work, life couldn't exist. The universe seems fine-tuned. Some physicists explain this with the multiverse idea. There are countless universes with different physical laws and constants. We find ourselves in one compatible with life, because that's the only type we could find ourselves in. The others exist, but there's no one there to wonder about them. String theory suggests something even stranger. There might be 10,500 different possible vacuum states, each corresponding to a different set of physical laws. Every possible universe might exist somewhere in this vast landscape. Our universe is just one possibility realized. But here's what strikes me as profound. Regardless of why this universe exists, it has a specific structure, and that structure is comprehensible. The fact that humans, complex arrangements of atoms that formed on one small planet, can understand black holes billions of light years away, can decode the curvature of spacetime, can predict the behavior of photons near event horizons, is miraculous. Mathematics works. The universe obeys laws. Those laws are elegant, often described by equations that fit on a single page. Einstein's field equations, which describe all of gravity and the large-scale structure of the universe, can be written as g underscore mu nu plus lambda g underscore mu nu equals 8 pi g c yt underscore mu nu. That's it. 10 coupled nonlinear partial differential equations that contain within them black holes, gravitational waves, the Big Bang, the expansion of the universe, the bending of starlight, everything. Why should reality be mathematical? Why should patterns we discover in our minds correspond to patterns in external reality? Eugene Wigner called this the unreasonable effectiveness of mathematics and the natural sciences. It's a mystery that might be deeper than anything physics can address. But let me tell you what I think makes this whole story beautiful. We started with a simple question. If light has no mass, why can black holes trap it? And answering that question took us through the nature of gravity, the structure of spacetime, the limits of knowledge, the origins of atoms in our bodies, the meaning of time, and the deep mystery of existence itself. That's what science does at its best. It starts with curiosity about one thing and reveals connections to everything else. It shows us that reality is far stranger and more beautiful than common sense suggests. It gives us tools to distinguish truth from comfortable illusions. And here's the most important part. None of this is complete. We don't have all the answers. Quantum gravity remains unsolved. Dark matter's identity is unknown. Dark energy is mysterious. The information paradox is unresolved. We don't know if string theory is correct or if some other approach to quantum gravity will win out. We don't know what the universe's ultimate fate will be. There's so much left to discover. Some of you watching this might be the ones who figure it out. Maybe you'll resolve the information paradox, or detect gravitational waves from the Big Bang, or discover the particle nature of dark matter. Maybe you'll develop the quantum theory of gravity that unifies everything. Maybe you'll find something we haven't even thought to ask yet. The story isn't over. The universe is still revealing its secrets. And every one of you can participate in that revelation, either by doing science yourself or by supporting it, by staying curious, by demanding that we keep exploring, keep questioning, keep pushing the boundaries of knowledge. Because ultimately, that's what separates humans from everything else we know of in the universe. We ask why. We're not satisfied with how things appear. We dig deeper. We build telescopes and particle accelerators and gravitational wave detectors. We do math. We make predictions. We test them. And slowly, incrementally, we peel back the layers of mystery. Black holes trap light because space-time geometry makes escape impossible. That's the answer. But the real treasure isn't the answer. It's understanding how we got to the answer, what it reveals about reality, and how many more questions it opens up. You now understand something that most people in human history couldn't have conceived of. You understand that gravity isn't a force, that space and time are unified, that the universe has a structure that goes far beyond what our senses reveal. You understand why Einstein is considered one of the greatest thinkers in human history, and why physicists are still working to extend his insights into new domains. That knowledge is power. Not power over others, but power over ignorance. Power to see through nonsense. Power to appreciate how special and strange existence is. Don't waste it. Let's get technical for a moment, because you've earned it. We've been talking about geodesics and curvature in conceptual terms, but let me show you what this looks like mathematically, at least in simplified form. A geodesic in spacetime is a path that extremizes the proper time, which is the time experienced by an object traveling that path. For a massive object, this is the path of maximum proper time between two events. For light, which experiences zero proper time, it's what's called a null geodesic. The geodesic equation in general relativity is d y x mu d plus gamma u underscore alpha beta d x alpha d tau d x beta d equals 0. Those gamma symbols are Christoffel symbols, which encode how the coordinate system is curved. They're derived from the metric tensor, which describes the geometry of spacetime. For a Schwarzschild black hole, the metric in Schwarzschild coordinates is d squared equals 1, 2 gm rc cy dt plus 1 twag mrc, 1 dr plus r squared, d plus sine d. That 2 gm rc term is crucial. When r equals 2 gm per c squared, the event horizon radius, weird things happen. The time and radial coordinates swap character. Outside the horizon, time is time-like and radius is space-like. Inside, radius becomes time-like and time becomes space-like. This is why you can't escape. Moving outward inside the horizon would be like moving backward in time, which is impossible. For a photon traveling radially near a black hole, we can derive that its trajectory satisfies Dr. dt squared equals c 1 twag m rc. At the event horizon, Dr. dt goes to 0 from outside. The photon can't escape. Inside, the equation shows that Dr. dt is always negative, choosing inward direction. The photon must move towards smaller r, toward the singularity. This is all consistent with the geodesic description. The math and the conceptual picture align perfectly. Spacetime curvature encoded in the metric determines geodesics, and geodesics describe all motion, massive particles, and light alike. Now, Schwarzschild black holes are the simplest case, non-rotating, uncharged. Real astrophysical black holes rotate, and rotation adds fascinating complications. A rotating black hole's geometry is described by the Kerr metric, found by Roy Kerr in 1963. Rotating black holes drag spacetime around them, an effect called frame dragging. Near a rotating black hole, you can't stay still. Space itself is rotating, carrying you with it. Rotating black holes have two event horizons and a region between them called the ergosphere, where you can extract energy from the black hole's rotation. In principle, you could throw something into the ergosphere in just the right way, and it would split, with one part falling in and the other escaping with more energy than you put in. The extra energy coming from the black hole's rotational energy. This is called the Penrose process, named after Roger Penrose, who discovered it. There's even a theoretical possibility of closed time-like curves near rotating black holes, paths through spacetime that loop back on themselves, allowing time travel to your own past. Whether these actually exist, or if quantum effects or other physics prevents them is unknown. The point is, Einstein's equations are incredibly rich. Every solution reveals new possibilities, new exotic objects, new ways spacetime can be structured. Black holes are just one class of solutions. There are also wormholes, solutions that connect distant regions of spacetime, though we have no evidence they exist and strong reasons to think they're unstable, even if they form. There are white holes, time-reversed black holes that eject matter rather than absorbing it, though, again, no observational evidence. And all of this comes from one insight. Space-time is dynamical. It responds to mass energy. It curves, and that curvature determines how things move. Newton thought space and time were absolute, unchanging backdrops against which events occurred. Einstein showed their participants, actors in the cosmic drama, not just the stage. That shift in perspective was revolutionary, and it's still shaping how we think about fundamental physics. Let me tell you about gravitational waves, because they're another consequence of space-time dynamics that relates directly to black holes. If space-time can curve, and if that curvature changes, then the changes should propagate at the speed of light. These propagating distortions are gravitational waves, ripples in space-time itself. Einstein predicted them in 1916, but they weren't detected until 2015, almost a century later. The Laser Interferometer Gravitational Wave Observatory, LIGO, consists of 2 detectors, one in Louisiana and one in Washington State. Each is an L-shaped vacuum chamber several kilometers long. Lasers bounce back and forth, measuring the distance between mirrors with exquisite precision. When a gravitational wave passes through, it stretches space in one direction and compresses it in the perpendicular direction. The effect is tiny, changing the detector's length by less than 1,000th of a proton's diameter, but LIGO can detect it. On September 14, 2015, both detectors saw the same signal, a chirp, a rising frequency and amplitude that lasted a fraction of a second. The signal matched the prediction for 2 black holes, 29 and 36 solar masses, spiraling together and merging 1.3 billion light years away. 3 solar masses of energy were converted into gravitational waves in the final moments, making it the most powerful event ever observed by humanity. For context, that's more power than all the stars in the observable universe combined, but released in a fraction of a second. Since then, LIGO and its European counterpart Virgo have detected dozens of black hole mergers, plus neutron star mergers. Rainer Weiss Kip Thorne and Barry Weiss won the Nobel Prize in Physics in 2017 for LIGO's development and the detection. Gravitational waves open a new way to observe the universe. Light can be blocked by dust, absorbed by gas, scattered by particles. Gravitational waves pass through everything almost unaffected. We can now see events that are invisible electromagnetically. And here's the connection to light and black holes. When 2 black holes merge, the event horizons briefly have complex, non-spherical shapes. Photons near those horizons follow incredibly complex trajectories, determined by the rapidly changing space-time geometry. Some photons orbit multiple times before escaping. Some fall in. The exact patterns depend on the observer's position and the black hole's masses, spins, and orientation. Simulating these scenarios requires solving Einstein's equations numerically on supercomputers. It's some of the most computationally intensive work in physics. But the payoff is we can predict exactly what gravitational waves should look like for any merger scenario, then compare to observations. Every detection confirms Einstein's equations in the most extreme environments imaginable. General relativity works from the weak gravity of Earth's surface to the strongest gravity in the universe, in colliding black holes. That's remarkable. But it doesn't work at the singularity. At infinite curvature, the equations break down. That's where we need quantum gravity. Several times today, I've mentioned quantum mechanics, but I haven't explained how it relates to our question about light and black holes. Let me fix that now. Quantum mechanics is the physics of the very small. At atomic and subatomic scales, particles don't have definite positions or velocities until measured. They exist in superpositions of multiple states simultaneously. Observation collapses the superposition into one definite outcome. The theory is probabilistic, giving only the odds of different measurement results, not certainties. Einstein hated this. He famously said, "God does not play dice with the universe." But every experiment ever done confirms quantum mechanics. Particles really do behave this way. Light exhibits quantum behavior too. We've done experiments where we send photons one at a time through a double slit, and they create an interference pattern, as if each photon goes through both slits simultaneously and interferes with itself. But if you try to measure which slit it goes through, the interference disappears. The act of measurement changes the outcome. This isn't an issue with measurement devices being too crude. It's fundamental. Quantum objects don't have definite properties until observed. This is called the measurement problem, and interpretations of quantum mechanics differ on what's really happening, but all agree on the math and predictions. Now, here's where it gets weird. General relativity is deterministic. Given the current state of spacetime and its contents, Einstein's equations uniquely determine the future evolution. There's no randomness, no probability. But quantum mechanics is fundamentally probabilistic. These two theories are both correct in their domains, but philosophically incompatible. One is deterministic, one probabilistic. One treats spacetime as smooth, one quantizes everything else. They both can't be the final story. Attempts to merge them into a quantum theory of gravity have been ongoing for decades. String theory is one approach. Loop quantum gravity is another. Both are mathematically sophisticated and make predictions. But we can't test those predictions yet because the energies required, the Planck energy, are 1,019 times higher than the Large Hadron Collider can achieve. But black holes might provide clues. Hawking radiation is a quantum effect in curved spacetime. The information paradox is a clash between quantum mechanics, information is conserved, and general relativity. Information seems to fall into black holes and disappear. Solving these puzzles likely requires quantum gravity. Recent work suggests something called holography might be key. The holographic principle states that all the information in a volume of space can be encoded on its boundary. For a black hole, all the information inside might be encoded on the event horizon. The horizon area, not the volume, determines the maximum information a region can contain. This has profound implications. It suggests spacetime might be emergent, not fundamental. The real degrees of freedom might be on boundaries, with spacetime and gravity arising from their entanglement. If this is right, asking what is spacetime made of is like asking what is temperature made of. Temperature is an emergent property of molecular motion. Spacetime might be an emergent property of something more fundamental. This is speculative, but it's where the cutting edge is. And it all comes back to understanding black holes, which means understanding how light behaves in extreme curvature, which means understanding the original question: why do black holes trap light? The answer has led us through classical general relativity, quantum mechanics, thermodynamics, information theory, and now to the frontier where physicists are questioning whether spacetime itself is fundamental. That's the power of a good question. It opens doors you didn't know existed. Let me tell you about Kip Thorne, because his work connects many threads we've discussed. Thorne is a theoretical physicist who spent his career studying black holes, gravitational waves, and general relativity. He co-founded LEGO with Rainer Weiss and Ronald Drever, though he focused on the theoretical predictions while others built the detectors. Thorne also consulted on the movie Interstellar, ensuring the depiction of a supermassive black hole was scientifically accurate. The black hole in the film, Gargantua, was rendered by solving Einstein's equations to trace how light would actually behave near a rapidly rotating black hole. The result was so accurate that Thorne and his team published academic papers based on the visualizations. The movie generated new scientific insights about photon trajectories near Kerr black holes. But here's what I find most inspiring about Thorne's career. He spent decades advocating for LEGO when many physicists were skeptical. Building detectors sensitive enough to see gravitational waves required technological advances that didn't exist when the project started. It required billions of dollars of funding over decades with no guarantee of success. Many thought it was a waste. Thorne persisted. He did the calculations showing what signals to expect. He advocated for funding. He recruited brilliant engineers and physicists. And in 2015, when the first detection came, it was vindication not just of Einstein's theory, but of Thorne's vision. That's how science works in practice. It's not just brilliant ideas. It's persistence, collaboration, engineering, politics, funding, decades of incremental progress. Einstein conceived general relativity in 1915. The first black hole candidate was found in 1964. Gravitational waves were detected in 2015. 100 years from prediction to confirmation. Science is a marathon, not a sprint. The truth doesn't reveal itself quickly. It requires patience, rigor, and a willingness to be wrong. And we're still wrong about many things. Dark matter, dark energy, quantum gravity, the arrow of time, the measurement problem, the nature of consciousness. These are open questions. Future generations will look back at our current understanding as incomplete, just as we look back at Newton's. But that's not a reason for despair. It's cause for excitement. There's so much left to discover. The universe is generous with mysteries. And here's the beautiful thing. You don't need to be Einstein or Hawking or Thorne to participate. You can support science by demanding funding for research. You can teach others what you've learned. You can stay curious and skeptical. You can raise children who ask why. You can vote for policies that value truth and evidence. Science is a collective enterprise. Every experiment, every observation, every calculation builds on what came before. You're part of that chain just by caring about truth. Let's talk about time for a moment, because it's central to understanding black holes and yet deeply mysterious. You experience time flowing from past to future. You remember the past, but not the future. Causes precede effects. Eggs break, but don't spontaneously reassemble. This is the arrow of time, and it's encoded in the second law of thermodynamics. Entropy, disorder, always increases. But the fundamental laws of physics are time-symmetric. Newton's laws, Maxwell's equations, Einstein's equations, even the Schrödinger equation of quantum mechanics, they all work the same running forward or backward in time. If you filmed particles colliding and played the film in reverse, it would still obey the laws of physics. So why does time have a direction in everyday life? Why do we age? Why do we remember the past and not the future? The answer seems to involve cosmology. The early universe had very low entropy. The Big Bang was a highly ordered state, all matter and energy compressed into a tiny volume. As the universe expanded, entropy increased. We're living in the aftermath of that low entropy beginning, surfing the wave of increasing entropy toward a high entropy future. The arrow of time emerges from this entropy gradient. Heat flows from hot to cold, eggs break, we age all because the universe started in a special state and is evolving toward equilibrium. But black holes complicate this picture. As Jacob Bekenstein and Stephen Hawking showed, black holes have entropy proportional to their event horizon area. When matter falls into a black hole, it seems to disappear, taking its entropy with it, which would violate the second law. But the black hole's horizon area increases, and its entropy increases by more than the matter's entropy decreased, so the second law is saved. This means black holes are thermodynamic objects. They have temperature, Hawking radiation, entropy, horizon area, and they can exchange energy with their environment. This is deeply strange. Entropy is usually understood as a measure of disorder or information, but a black hole's entropy depends only on its horizon area, not on what's inside. This led to the holographic principle I mentioned earlier. The maximum entropy in a region equals the area of its boundary divided by 4 Planck areas. Volume doesn't matter. Area is what counts. This is bizarre and suggests something profound about the nature of spacetime and information. If holography is correct, our three-dimensional experience might be a projection of information encoded on a two-dimensional boundary at the edge of the observable universe. We might be living in a hologram. This sounds like science fiction, but it's a serious idea in theoretical physics, supported by calculations in string theory and studies of black hole thermodynamics. It hasn't been proven, but it's a leading candidate for how quantum gravity might work. And it all connects back to black holes trapping light. The event horizon isn't just a boundary beyond which light can't escape. It's a thermodynamic surface, an information boundary, possibly the most fundamental object in the universe. Understanding why light is trapped led to understanding black hole thermodynamics, which led to holography, which might revolutionize our understanding of spacetime. One question, endless implications. I want to address something you might be thinking, does any of this matter to my daily life? I'm not a physicist. I'll never visit a black hole. Why should I care? Fair question. Let me give you several answers. First, practical applications. General relativity isn't just abstract theory. GPS satellites require relativistic corrections. Without accounting for time dilation, GPS would be off by miles within hours. Every time you use navigation, you're benefiting from Einstein's insights about spacetime curvature. Gravitational wave detection is leading to new sensor technologies. Understanding extreme physics drives innovation in materials, computing, and engineering. Historically, curiosity-driven research has led to countless practical applications. Quantum mechanics gave us semiconductors and lasers. Nuclear physics gave us medical imaging and cancer treatment. Relativity gave us GPS. You can't predict what fundamental research will yield, but history shows it yields plenty. Second, cultural value. We explore space for the same reason we create art. Because we can, because it's beautiful, because it expands human experience. Understanding black holes is like understanding Shakespeare or Beethoven. It enriches life even if it doesn't pay the bills. Third, existential preparation. Humanity faces challenges that require scientific thinking. Climate change, pandemics, asteroid impacts, artificial intelligence. Cultivating a society that values evidence, logic, and curiosity isn't just nice. It's necessary for survival. Understanding black holes might seem irrelevant to climate change, but the mindset that lets you understand black holes questioning assumptions, following evidence, building models, testing predictions, is the mindset we need for every major challenge. Fourth, meaning. Many people find purpose in religion, art, relationships, work. Science offers another path, understanding your place in the cosmos. You're made of atoms forged in stars. You're standing on a planet orbiting a star in a galaxy containing billions of stars and likely billions of planets. You're conscious, capable of understanding the laws governing all of it. That's profound. That's meaningful. For some people, myself included, understanding the universe is deeply fulfilling in ways that aren't reducible to practical applications. You don't need to become a physicist, but appreciating what physics has revealed, understanding that reality is stranger and more beautiful than common sense suggests, recognizing that humans can decode nature's deepest secrets, that's worth something. And finally, legacy. What we do echoes in time. The physicists who built the foundation for modern science, Newton, Maxwell, Einstein, Bohr, Heisenberg, they're dead, but their ideas live on. They changed how every human afterward understands reality. By learning about their discoveries, by teaching others, by supporting science, you participate in that legacy. You're part of the unbroken chain of humans who looked at the stars and asked why. That matters. It matters a lot. Let me bring this home with a thought experiment. Imagine you could observe someone falling into a black hole from a safe distance. You watch them approach the event horizon. As they get closer, they appear to slow down, redden, and fade. From your perspective, they never quite reach the horizon. They asymptotically approach it, becoming dimmer and more red-shifted until they're invisible. But from their perspective, they cross the horizon in finite time. Once across, they see the singularity in their future, unavoidable. If they look back, they see the outside universe blue-shifted, accelerated. They see stars being born and dying, galaxies colliding, the entire future of the universe compressed into their final moments. Both perspectives are real. There's no contradiction because they're measuring different things in curved spacetime. Your coordinate time isn't their proper time. Now here's the question. After they cross the horizon, do they still exist from your perspective? You never see them cross. The last photons they emit take infinitely long to reach you. Does that mean they're stuck at the horizon forever in your reality? No, they crossed. The horizon isn't a physical barrier for them. It's just a coordinate singularity in your reference frame, a place where your coordinates break down, but nothing special happens locally. This is similar to the relativity of simultaneity in special relativity. Two events can be simultaneous in one reference frame, but sequential in another. Both perspectives are valid. There's no absolute truth about which happened first. In general relativity, the situation is even more complex. Different observers carve up spacetime into space and time differently. Your now is different from someone else's now, but the underlying spacetime structure, the block universe, is absolute. All observers agree on spacetime events, just not on how to slice it into space and time. This has implications for the nature of existence. Do things that exist in your past still exist? If the block universe is real, yes. Your childhood self is a real part of spacetime, just as real as your current self. The fact that you can't interact with it doesn't make it less real. Similarly, your future self exists in spacetime. You can't access it yet, but it's there, woven into the fabric of reality. This view makes death less absolute. Your life is a world line through spacetime, a four-dimensional structure. The fact that your world line ends doesn't erase it. You'll always have existed in the segment of spacetime you occupied, just as a character in a book exists in certain chapters, even if they die before the end. Now, I'm not saying this should console you about mortality. That's a personal, emotional matter, and physics doesn't prescribe how to feel. But it does offer a different perspective on existence. You're not a temporary blip. You're a permanent feature of the universe's history. Your world line intersected with countless others. You affected people, events, the flow of causality. Those effects propagate forward in time. In a real sense, you echo in the future, even after your world line ends. This is as close to immortality as physics offers. You're a permanent part of the causal structure of the universe. And understanding black holes, understanding how space-time works, understanding why light is trapped, that understanding becomes part of your world line, part of what you contributed to the universe. Every thought you have, every action you take, every person you influence becomes part of the tapestry. Make it count. We're nearing the end of this journey, and I want to tie everything together. We started with a simple question. If light has no mass, why can black holes trap it? The answer: gravity isn't a force pulling on mass. It's the curvature of spacetime. Mass energy causes curvature, and objects follow geodesics through curved spacetime. Light, despite having no mass, follows geodesics like everything else. Near a black hole, spacetime is curved so severely that all geodesics lead inward past the event horizon. Light is trapped not by being pulled, but by having nowhere else to go in the structure of spacetime itself. This answer opened countless doors. We explored general relativity, the nature of spacetime, black hole thermodynamics, gravitational waves, quantum mechanics, holography, the arrow of time, and the meaning of existence. One question, an entire universe of implications. That's what I love about physics. It's not isolated facts. It's a web of interconnected ideas, each one supporting and illuminating the others. Pull one thread, and you find it connects to everything. And we're not done. Future physicists will extend these ideas further. Maybe they'll solve quantum gravity. Maybe they'll discover new kinds of black holes or exotic objects we haven't imagined. Maybe they'll unify all forces and explain dark matter and dark energy. Maybe they'll find we're living in a simulation or a multiverse or something stranger still. The adventure continues, and you're part of it, even if you never publish a paper or build a detector. By understanding, by caring, by sharing what you've learned, you participate in humanity's greatest project, decoding reality. Before we end, I want you to do something. Go outside tonight if the sky is clear. Look up. Find a bright star. The photons hitting your eye left that star years ago, traveling through space at 186,282 miles per second, following geodesics through curved spacetime, dodging planets and black holes, until finally, after an incomprehensible journey, they entered your eye and triggered chemical reactions in your retina that sent electrical signals to your brain that became the experience of seeing light. You're connected to that star by geodesics. You're part of the same space-time fabric. The same laws that govern black holes trapping light govern your perception of that starlight. You're not separate from the universe. You're a piece of it, looking at itself, understanding itself. That's miraculous. Thank you for spending these 3+ hours with me. Thank you for your curiosity, your attention, your willingness to have your intuitions challenged and your worldview expanded. If you enjoyed this video, if you learned something, if you felt that sense of wonder that comes from understanding something profound, do a few things for me. Like this video. It helps the algorithm show it to others who might appreciate it. Subscribe to this channel. I create deep dives like this on topics that matter, that challenge, that illuminate. Share this with someone. Teachers, students, friends, family. Anyone who's ever looked at the night sky and wondered. Anyone who's asked questions without being satisfied by simple answers. And most importantly, stay curious. Keep asking why. Keep learning. Keep pushing your boundaries. The universe is vast and strange and beautiful. We've barely scratched the surface. There's so much more to discover, to understand, to marvel at. And every one of you has the capacity to be part of that discovery, whether as a scientist, a teacher, a supporter, or simply as someone who cares about truth. Don't let anyone tell you science is dry or boring or irrelevant. You've just spent 3 hours learning why black holes trap light, and along the way, you've encountered mysteries as profound as any philosophy, beauty as striking as any art, and stories as human as any history. Science is humanity's grandest adventure, and you're invited. Now go out there and share what you've learned. Tell someone why black holes trap light. Blow their mind the way yours was blown. Because understanding is meant to be shared. And the more people who understand, the better equipped we are to face whatever challenges and opportunities the future holds. The universe revealed a secret to you today. It showed you how light and gravity and space-time and black holes all fit together in a cosmic dance of mathematics and meaning. Honor that gift, use it, share it, build on it, and never, ever stop wondering why. Thank you for joining me on this journey through space-time. Until next time, keep looking up, keep asking questions, and keep seeking truth